Good day, dear participants of the workshop. With your permission, I present a work, Hybrid Neural Network Identifying Complex Dynamic Objects, Comprehensive Modeling and Training Method Modification. Experimental research and modeling, particularly for complex dynamic objects like helicopter turboshaft engines and their control systems, are integral across the entire life cycle from design to disposal. The development of the industry heavily relies on digital technologies, including digital manufacturing, computer modeling, machine learning, and cloud computing, with the implementation of digital twins to virtually represent physical objects throughout their life cycle, while semi-natural modeling integrating real systems with mathematical models has been employed across various industries, ensuring the adequacy of complex dynamic object models and control system poses ongoing challenges, prompting the need for adaptive models identified by real-time characteristics and operating conditions, with intelligent technologies like neural network playing a significant role in addressing these complexities. Neural networks are an effective means of solving a wide range of tasks in complex dynamic objects identifier and their control systems. A common disadvantage of most known solutions is requirement for the completeness of processed samples. The research aim is to increase the efficiency of complex modeling and testing of a real automatic control system for complex dynamic object monitoring and diagnostic through the use of nonlinear dynamic mathematical models and their system in the form of neural networks, using the example of helicopters' turboshaft engines. To solve the above task of complex dynamic objects and their control systems, an intelligent system can be used that implements the fault detection and identification methods, FDI. It is based on a neural network mathematical model of the research object and an identification block. The mathematical representation of the nonlinear dynamic model of complex dynamic objects can be represented in this differential equation system. The use is justified by a modified version of a recurrent multilayer perceptron, NARX. It is a dynamic network characterized by the delay of output-input signal combined in a network input vector with a radial basis on nonlinear and a linear recurrent layer. It should be noted that in no researches uses a Gaussian NARX framework with an input data regressor selection using a modified gradient method. This modification is justified based on the outdated NARX models with outdated machine learning methods. The proposed modified NARX structure consists of two parts, nonlinear and linear blocks. A scientific concept of direct construction of a neural network model of complex dynamic objects is proposed in this work. The method of calculating the elements of the Hessian matrix, a component of the analytical expression of the Levenberg-Marquardt methods, was future developed, which, by taking into account the weight connection of neurons of both nonlinear and linear layers, allowed to reduction of the calculation time by approximately 10-11 times compared to the central difference derivative. The use of direct calculation made it possible to reduce the calculation time by approximately 2.07 to 0.14 times compared to the central difference derivative. To conduct a computational experiment, the TV3117 turboshaft engine was selected as a research object. The input parameters for the mathematical model of the helicopter turboshaft engine include atmospheric values, and the helicopter onboard parameters are normalized to absolute values based on the gas dynamic similarity theory. To address the challenge of the local minima is complex dynamic objects identification tasks, two heuristics approaches were developed and tested. The first involves taking risky steps in random direction along the error surface with increasing step length to escape local minima, while the second employs a modified genetic algorithm to navigate the search space more effectively, both demonstrated through testing on multiplayer data sets and compared against conventional methods. LabVIEW created specialized software that used a modified Levenberg-Marquardt algorithm and automated the recording of experimental results. The program implements the following single-threaded and parallel options: the traditional Levenberg-Marquardt method with the calculation of loss function using the central difference, the derivative expression; the modified Levenberg-Marquardt method with the calculation of loss function by the Broyden method once every two epochs with the two heuristic approach described above; the traditional Levenberg-Marquardt method with the calculation of loss function using analytically derived expressions. The computational experiment aims to assess the execution time of each method, considering the proposed methods for calculating the Jacobian matrix for training a NAIX hybrid network with 7 inputs, 20 neurons in the nonlinear layer, 5 neurons in the linear layer, and 1 neuron in the output layer was used. To assess the quality of training, the instantiation functional is used. The calculation results are presented in this table. Using of training sample identification errors were obtained for the following parameters of the TV3117 turboshaft engine: the degree of increase in the total pressure in the compressor, top left figure; compressor turbine shaft power, top right figure; compressor turbine operation, bottom left figure; fuel consumption in the combustion chamber, bottom right figure, where yellow line, error obtained by the NAIX hybrid network with the classical Levenberg-Marquardt methods, red line, error obtained by the NAIX hybrid neural network with the modified Levenberg-Marquardt methods, green line, approximation line. This table contains the results of a comparative analysis of the accuracy of identification of thermogas dynamic parameters of the engine operating process using a neural network and classical methods for each parameter of the TV3117 turboshaft engine model, and the outcomes of computing the coefficients for both erroneous and quality identification of parameters, including the relation between the dependence of the degree of increase in the total pressure in the compressor, compressor turbine shaft power, compressor turbine operation, and fuel consumption in the combustion chamber. The conclusions are presented on this slide. Thank you for attention.